Hello, Calc 3 friends. I'm going to make a video to finish up 17.6 and then talk about Stokes and divergence theorem. And so last time we were talking about flux integrals, and so remember what a flux integral is. It kind of records how much of your vector field is going perpendicular to your surface S. And so it's the total flux of the surface. And the way you compute it is you need to generally parameterize your surface, and then you can do the integral over kind of the region in the UV plane of f dot uh, your normal vector, which is the tangent vector with respect to u cross tangent vector v. And then this should be not dot, but just times dA. And so we were trying to compute the flux of the radial vector field, which is x, y, z. And we want to do it across the hemisphere and also across the paraboloid. And so what we want to do is we want to just kind of look at what their flux is on these top surfaces. I started doing the hemisphere one, and I realized that the way that I did it using this kind of spherical coordinate parameterization leads to this really, really disgusting integral. And it's actually not the way to go about doing it. And so I'm going to cancel this out, and we're going to redo it. And we're going to actually use an explicitly defined kind of way of doing it. So the explicit form of hemisphere is given by z, well, technically it's implicit, but z squared plus y squared plus x squared equals 1. And so the idea is that the normal vector for the explicit form of this, the normal vector n, is given by you take the negative z sub x, negative z sub y, 1. And where I'm getting that from is if we go back here, right here, let f be a continuous function on a smooth surface, then the surface integral of anything, or so technically this is with an explicit, but where this comes from is because the normal vector uh, for an explicit description of a function is negative zx, negative zy, 1. And so that's how you can get a normal vector from that. And so that's a trick we're going to use to find normal vectors. It comes from the fact that if you kind of solve for this and have a description as, so where it comes from is if you had a description of R using X and Y, which I say we shouldn't do, but they do it anyways, where the description of your is just X and then Y and then G of X, Y. If that's the description of your kind of parameterized surface where X and Y are just what they are themselves, and then that's your surface Z, then if you take the tangent vector with respect to X, you get 1, 0, and then Z with respect to X. And then so real quick kind of where this comes from. So T, I guess sub X, it should be T sub X. What's this equal to? It's going to be 1, 0, and then Z sub X. And then what's T sub Y going to be? It will be 0, 1, and then Z sub Y, because Z is equal to, so if Z is equal to G of X, Y, you can do it like this. And then you take their cross product. And so then TX cross TY will equal, I will spare you the details, but if you take their cross product, this is what the normal vector is. This is negative zx, negative zy, 1. And so that is our normal vector. And so this is n. So n is equal to that. So negative zx, negative zy, and 1. And so whenever you have an explicitly defined function, which technically this isn't an explicitly defined function, but we could easily do it by just solving for z, right? And explicit, this is the normal vector. And so we need to find zx and zy, but we can actually use implicit differentiation here to find them. And so z sub x is you just take the partial with respect to x of that function. So z squared plus y squared. I guess, sorry, let me just do it like this. Let's do it. I could solve for z and then do it, but I think it's just easier if I do it using implicit differentiation. So take the partial with respect to x of both sides, and you get 2z times z sub x, because that's the chain rule. Then the partial with respect to x of y is 0, and then plus 2x. And then that is equal to 0, and then we can solve for z sub x. So then z sub x is equal to negative x over z. You can do a very similar thing to get that z sub y, and so I'll just skip it, but z sub y was going to be the exact same thing. It's going to be negative y over z. And so our normal vector is going to just be, you take the negatives of those, so it's x over z, y over z, and 1. So that's the normal vector to any point on the top of our hemisphere. And another place you could see that is also in this table. If you go to the sphere and you look at the normal vector, it's x over z, y over z, 1. And so that's our normal vector. Once we have our normal vector, we can dot it with plugging in this into the vector field. And so our vector field f, when I plug in the parameterization, really r of x, y, what is that equal to? It's equal to plug in what is our function that we're dealing with? We're dealing with this guy. And so I think in this one, we are going to have to do it. It was x, comma y, and then comma z. And so z in this case is 1 minus x squared minus y squared square root. And so that's our vector. And so then we need to do f dotted with n will equal. So I dot these two guys, I get, it looks like x squared over z plus y squared over z plus square root of 1 minus x squared minus y squared. And then the x and y's for which this is true are the x and y's in the unit circle, because that's the projection down here. And so the double integral over this surface of f dot n d capital S is going to be instead the double integral over the projection of this dot product, which is x squared z plus y squared z plus square root of 1 minus x squared minus y squared dA. And so this needs to be in terms of x and y, though. And so we have to replace what z is here and there. And so this becomes, using what we just solved for z, this will be the double integral over the region R, which R is the unit disk, of x squared plus y squared over z, which was the square root of 1 minus x squared minus y squared, plus square root of 1 minus x squared minus y squared. Minus y squared dA. And now what we're going to do is we're going to use polar coordinates to make this a lot easier. And so convert to polar coordinates. So convert to polar, to polar. And so as we convert to polar, we get the double integral over the unit disk, which the unit disk in polar coordinates is 0 to 2 pi, 0 to 1. X squared plus y squared is just r squared. And then this is going to be over square root of 1 minus r squared. And then plus, this becomes the square root of 1 minus r squared. And then you have to multiply this whole thing by r dr d theta. And then we're going to do one more little algebra trick to kind of simplify this. So I'm going to rewrite this as multiply top and bottom by 1 minus r squared. And then this goes away because I squared it. And then I can combine it into one fraction. And then this and that will cancel. And so this should simplify quite nicely to 0, 2 pi, integral of 0, 1. And then it just becomes r on top, and on the bottom is the square root of 1 minus r squared dr d theta. And now I can do substitution. U equals 1 minus r squared. So when r equals 0, that implies that u equals 1. And when r equals 1, that implies that u equals 0. And so it will be the integral, and then du, I guess we should compute what that is. That's going to be minus 2r. And so it becomes the integral from 0 to 2 pi, plugging in those things, integral from 1 to 0, and then it'll be, oh, this should be a dr, by the way, negative 1/2 u to the negative 1/2, and then du d theta. Because then, yeah, because dr is negative 1/2 du, so that's good. And then this is just the integral of u to the negative 1/2. So that all looks good. And then now I can integrate. So I'm just going to turn the integral for the theta just to 2 pi. 2 pi times, and then you add 1/2, and so it's u to the 1/2. It's going to be negative 1/2, evaluated from 1 to 0, and then u to the, well, I guess I can just evaluate it. So you add 1, so it's u to the 1/2 times 2, so times 2u to the 1/2, and then evaluated from 1 to 0. If you plug in 0, you get 0, and then we subtract 1, you get 1, and so this is just going to equal 2 pi. And so that's a lot of work. And so, but this is kind of showing you what you can do for a flux integral through the surface when it's explicitly defined. And so let me just remind you of that formula. So the formula to do the double integral over a surface of f dot n ds, where let's say that f is given by, f, g, has some component functions f, g, h, and let's say it's an explicitly defined surface, so it's z equals, I guess I shouldn't use g here. What did they use? Yeah, maybe z is explicitly defined as, I don't know, I don't know what letter to use here. G, capital G, X, Y, I guess. I don't know. So it's an explicitly defined surface. Then the normal vector for an explicitly defined surface is negative z sub x, negative z sub y, and then 1. And so then this integral becomes the double integral over the projection in the xy plane of if you do f dot n, if you dot these two vectors, you get negative z sub x times the function f plus, I guess, minus z sub y times g, and then plus h, and then dA. And so this is how you would evaluate it, and that's what we just did. And so we computed what this is and multiplied, computed that and that. And then to actually evaluate it, you need to just make sure that these guys end up being in the variables that your dA is in. And so in this case, we want it in terms of x and y. And so if you have z, you need to return it. And so that'll come up when we do Stokes theorem in a little bit, but that's how you do that one. Now let's also do the paraboloid. So z equals 1 minus x squared minus y squared. So that's this guy. And I'm just going to tell you what the parameterization is. So you're going to want to come up here. And so for a paraboloid in general, you're going to do a parameterization of, so this is, or sorry, right here, this parameterization, v cosine u, v sine u, v squared. So that's like if it's facing up, but because ours is upside down, it's still going to be v cosine u, v sine u, but then instead of being v squared, it's going to be 1 minus v squared so that it's going downwards. And so that's the parameterization we're going to use. And I'll just say this parameterization is much harder than anyone I'll ask you to do, but it just makes the problem easier. And so we're going to do it. So for the paraboloid, we'll use, and so if I gave you one of this difficult, I would just give you the parameterization. So let's start with the parameterization. RUV equals, I believe we want v cosine u, v sine u. That represents a unit circle or a circle of radius v, which paraboloids at every kind of v slice where v is kind of representing our z is going to do that. And then it's going to be 1 minus v squared to make sure that we get the upside down part of it. And this is going to be for 0 is less than or equal to u is less than or equal to 2 pi. That gives us kind of our theta. And then our v is representing our z values. And so our z values go from 0 to 1. And so at 0, we're at the top, and then they go down to 1. And so 0 is less than v is less than 1. That's the parameterization we're going to use. For this parameterization, we can compute tu cross tv. So tu is going to be, take the partial with respect to u, and you get negative v sine u, v cosine u, and then taking the partial with respect to u gives me 0. And then TV, if I take the partial with respect to V, I get cosine U, sine U, and then dV would be negative 2V. And so then I want to take their cross product, TU cross TV. And so it's IJK. And the partial with respect to U was negative V sine U, V cosine U, and then 0, cosine U, sine U, and negative 2V. And so if we take that cross product, the first component will be negative 2V squared cosine U. The second component, if I cancel out this, will be positive 2V squared sine U, but because it's minus in the second component, it's going to be minus 2V squared sine U. And then the third component will be minus V sine squared U minus V cosine squared U. And so that just becomes minus V. And so this is minus 2V squared cosine U minus 2V squared sine U, and then minus V, because sine squared plus cosine squared equals 1. So that's our tangent vector. We need to plug in, we need to plug F evaluated at that. And so F evaluated at R of UV is really just R of UV. And so it's V cosine U, V sine U, and then 1 minus V squared. And then we're going to dot it. So I'm just going to skip to that. And so we want to integrate over that surface, which is the upside down paraboloid of our vector field dotted with the normal vector D capital S. And so it's going to be the double integral instead over the projection, or not the projection, actually, this region in the UV plane of what will it be? We dot this guy and this guy gives me negative 2V cubed cosine squared U. Then this guy times this guy gives me minus 2V cubed sine squared U. That's convenient because that's going to cancel. And then dotting this guy and this guy gives me minus V plus V cubed dA. And so it will be du dV, but we'll have to switch it over. Then what do? We'll simplify this down and we'll just evaluate. So U goes from 0 to 2 pi. V goes from 0 to 1. And then it becomes minus 2V cubed plus V cubed. So that's just minus V cubed. Minus V cubed. And then minus V. dV du. And so du just becomes 2 pi. And then times the antiderivative of this, which would be negative V to the 4th over 4 minus V squared over 2, evaluated from 0 to 1. And if I plug in 1, I'll get a 4th minus a half. So minus 1/4 minus 1/2. If I plug in 0, I get 0. And so what is that? This is times 2 pi. And so that will be 3/2? No. Minus 3/4. 3/4. And so it's 2 pi times negative 3/4, which will be negative 3/2 pi. And so the issue is that our flux is negative, and so that doesn't quite make sense. And so this is something that might happen when we compute these tangent vector or these normal vectors. Because if we look at this picture, our radial flow is going out. It's facing out, right? The vectors are going out, and our normal vectors should also be facing out. And so this flux should be positive. It shouldn't be negative, because negative would mean that it's coming, like the vector field is going opposite the outward facing normal, but that's not the case because it's radially pointing out. And so what must have happened is because of the way this is parameterized with 1 minus V squared, so it's kind of starting at the bottom and going to the top, then the way that I cross product these guys is actually going to give me the inward facing normal. And so I can just, so if you get a negative, you can just kind of use the thing that's nice about whether you pick the inward facing normal, outward facing normal, it will only affect your problem by a minus sign. And so if you get a negative flux, just kind of look at the problem and see if it should have been negative. And in this case, because we know that radial outward is going outward and it should match the outward, we can switch it. So flux should be positive, positive. So it is 3 pi over 2. Because, and the reason it's positive in this case is because the vector field is radially pointing out, so it should go in the same direction. And so that's finishing up 17.6. And so go ahead and look at these problems, and then I'll make a video for 17.7. All right, have a good one.